This lesson is about how to draw the ray diagram for mirrors. There are a few concepts about mirrors to remember when we do these ray diagrams. The point is to determine where the image will form. By doing the ray diagrams, we can then describe some attributes of that image. When doing these ray diagrams, there are some basic assumptions. First, there is a midline called the optic axis, which bisects the mirror. When we did waves, we called this the equilibrium line. All of the reflected rays will travel in straight lines, both the ones going from the image to the mirror and the reflected ones coming off the mirror. The top of the image is that point where these reflected rays all meet up together or converge. There's a difference between real images and virtual images. Real images are always upside down or inverted. They extend from the optic axis down. These will form in front of the mirror, which is why they can be projected. Virtual images are always upright, meaning they go from the optic axis up, much like the object does. And these will form inside or behind the mirror and cannot be projected. If the height of the image is less than the height of the object, then that image is said to be reduced. If the height of the image is greater than the height of the object, that image is said to be enlarged or magnified. If the heights of both the image and the object are the same, then there is no magnification, and that's the attribute given for that image. Okay, now let's talk about the two lines that are going to be drawn. We will draw two lines from the object to the mirror to determine where they converge so that we can draw in the image. The first light ray will extend from the top of the object parallel with the optic axis to the mirror. The reflection from the mirror will go from that point through the focal point. The second line is the opposite. It goes first from the top of the object through the focal point to the mirror and then is reflected back parallel to the optic axis. You'll notice this is the point of convergence. So the image is drawn from the optic axis to wherever that point of convergence is. From that, you determine the attributes. Sometimes this image is shorter than the original object. It's said to be reduced. Sometimes that image will be larger and that object is said to be magnified. If this point of convergence is such that the image forms above the line, then we know that that would be a virtual image. In this case, because it's inverted, we know that it is a real image. When we get to convex mirrors, we will have to extend these lines into and beyond the mirror to determine where the image is going to form. Those also will be virtual images. Okay, let's do a couple of samples. We have a triangular object here in front of a concave mirror. The light rays that we will explore will go from the top of the image parallel to the optic axis, then reflect back through the focal point. So let's draw that. It goes from that point down to the focal point. That's the reflected ray. Just go ahead and extend it. The second one goes from the top of the object through the focal point and then reflects back parallel to the optic axis. This point right here, my lines aren't perfect, but that point right there is the point of convergence. So our object, let me pick a different color here, is going to extend from the optic axis to that point of convergence. So that would be the image formed. The attributes, write that word down. The attributes or properties of that image would be that it is reduced, because you'll notice that our image triangle is shorter or smaller than our original object triangle. So it's reduced. it is upside down, so we say it's inverted. And all inverted images are real images. Those are the three attributes. All images will have three attributes. Let's do another one. This is a convex mirror, so it's a little more tricky because the light can't actually go through the mirror, can it? So when the light goes parallel to the optic axis and hits the mirror, it actually diverges away, right? So what we want to do then is draw an extension of where it would go from the point where it hits the mirror down through the focal point, like this. And we just extend it into the mirror, or behind the mirror. Alright, let's do the other one. So the other one, if it were going from the top of the object toward the focal point, it could get that far, and now it's going to hit a solid object and reflect back out. And we know that light that hits a convex mirror diverges. So in this case, it diverges parallel to the optic axis at that point. As far as our image goes, we've got to extend that line beyond the mirror. Now, our image is going to form right where these 2 points meet. Not a very good smiley face. We can see what the attributes are at this point. We can see that it is reduced, right? Because our new little smiley face is smaller than the original. It is upright. And then we have 2 pieces of evidence that tell us that it is virtual. Our 2 pieces of evidence that it's virtual are that, one, it's inside the mirror, and the other is that it's upright. On these, of course, there would be more rays of light. There would be an infinite number of rays of light coming, hitting the mirror and diverging off. However, it's really only these 2 that give us our best evidence about where the image is going to form. Parallel and to the focal point and parallel. So with this, I've given you a practice worksheet. Much like the examples I just worked, you're going to draw the 2 rays, parallel to the optic axis and then back to the focal point, and through the focal point to the mirror, and then back parallel to the optic axis. From that, you'll be able to decide the 3 attributes. Your image will either be real and inverted, or virtual and upright. After those 2 attributes, you'll have to determine if your image is magnified, enlarged, or reduced. So, let's work a couple of these. Here's our object. The top of the triangle is where we begin. We're going to go parallel to the optic axis and then back through the focal point. Then we're going to go through the focal point and parallel to the optic axis, and try to do these as straight as possible. So the point of convergence right here is where the top of our image will be. So it's going to go from the optic axis, and then instead of going up like the object, it's going to go down. I wonder if I can fix that. Hang on. There we go. Okay, so good thing about iPads, right? Cut and paste. So we can see that our triangle, it's pretty close to the same size, but if we were to measure it from top to bottom, if our lines were perfectly straight, I think that because this object is to the left of the center of curvature, that we can already predict that it's reduced. It's barely reduced, but it still counts as reduced. It's not exactly the same size. Hopefully on the test I'll give you examples that are a little more clear. Okay, we know that it's inverted. We can see that it's upside down. And because it's inverted, the fact that it formed in front of the mirror. Some of these attributes are just givens. Just memorize them. Now in this example, our object is at the center of curvature. And you'll find that we're going to have some predicted attributes of the image that forms. Okay, so let's draw the line parallel to the optic axis and then reflected back through the focal point. And then the second one goes through the focal point to the mirror, and then from the mirror reflects back parallel to the optic axis. Now, looky here. The image formed is at the same point. it also is the same size. So what we find is that there is no magnification. M is equal to 0 for this. It is inverted. It is real. But there's no magnification. It's not enlarged. It's not reduced. It's the same height. So the height of the image equals the height of the object. And that will be true every time the object is at the center of curvature, distanced for that mirror. Here we have an object that is between the center of curvature and the focal point. Let's draw the rays and see what happens to our image. Parallel to the focal point, through the focal point and parallel. Okay, I hope that you can tell that the reflected image is actually a little bigger than the original object. So this object is enlarged. Or we could say it's magnified. Okay, it is inverted, making it a real image. And those are the attributes of that image. This will be true every time the object is located between the center of curvature and the focal point. It will be enlarged. Now here we have a unique situation. Here we have the object at the focal point. Let's see what happens to the ray diagrams here. So our first ray goes parallel to the optic axis and back through the focal point. The second one, which needs to go from the top of the object to the focal point, winds up going like this. So our point of convergence is right here on the optic axis at the point of the object. So here are the attributes for this. There is no image formed. That's how you can use mirrors to make something disappear. Have the object be at the focal point of the mirror, and then you can't even see an image. That will be true every time the object is at the focal point. Okay, we have the convex mirror. What makes the convex mirror tricky is the fact that we've got to extend lines into the mirror. But we're still going to go parallel to the focal point and to the focal point and parallel. Here's our first ray, parallel to the optic axis. Now we're going to aim for the focal point. Even though we know that the real ray in that same plane is diverging off the front of the mirror. The second one is a little more tricky. So you're going to have to aim from the top of the object over here to the focal point, even though the ray doesn't go through the mirror. But we got to head it in that direction. There it is, heading to the focal point. We know that at this point it really reflects back, and this way it reflects back parallel to the optic axis. But the ray that we're going to extend will go into the mirror parallel to the optic axis. Now, point of convergence, right there. So our image is going from the optic axis up to the point of convergence. And now we can describe the attributes. We have an image that is reduced because you'll notice that that arrow is shorter than the arrow representing the object. It is into the mirror, so it is virtual, and it is upright. Another piece of evidence that it's virtual, because all virtual images are going to be upright. Otherwise, a makeup mirror wouldn't work, right? We'd be looking at ourselves upside down. It's the positioning of the object to the convex mirror that determines whether or not that object will be enlarged or reduced. Some are enlarged, some are reduced. Okay, here we go. Ray diagrams. Have fun with it. Remember, there are just two rays, parallel to the focal point and through the focal point and parallel. Then we know where the image forms and in what direction it points. If it's inverted, it's a real image. If it were upright, it would be a virtual image. And it's the height of the object that determines whether or not it is magnified or reduced. Good luck with your ray diagrams.